Hello everyone, my name is Mengchhay. Today I will show you how to use PermaLearn, a 2D structure analysis tool. Let's go straight into it. The first component called calculator is used to calculate a force that have rotational angle like this one, and it will calculate the horizontal and vertical load for you, as you can see here. For the grid size, it's used to make the grid bigger or smaller depending on the exercise that you will face. For the finite element, the more thing you add, it will contribute to how much it go up. So when you add more stuff, the finite element will go up, and when it is maximum, you cannot add anything anymore. For the Mengchhay, I will explain it at the solution tab, and this is just the system, unit system, SI, and British system. Now I will show you how to add member. For beam, just go to the horizontal distance and add a number. 5 meter beam, and vertical is the column, so 5 meter column. And if you want a frame, just add both horizontal and vertical. And for this, it's just a coordinate, the beginning one, which is 0, 0. If you want to add it, you can also add it like this. And you can add another beam. For join, you choose what join to start from. So when you don't want to use the begin XY coordinate, you can just use join to add something like this one. So I can continue adding this. Now let's move on to support tab. This one, it's simple, just choose a joint, add the support. There are 3, fixed pin and roller. You just choose it and you put it. Put it like the exercise want you to. It's depend on the exercise. It could be fixed, roller, or pin. Now let's move to hinge tab. A hinge transfers shear and actual load but does not transfer bending moment. Usually, for truss exercise, we need to add hinge for all member. For normal exercise like beam column, the exercise will tell you which part need to add hinge. So let's say the exercise here tell us that D is a hinge, so we just add it like this. For joint loads, it's really simple. Just choose a joint wherever you want. Just you can add load, vertical, horizontal, or even moment, or you can add all at once. It depends on the exercise. For point load, this is a bit complicated than the joint load, but let's say you forget to add joint and you want to add force in the middle here, so you just choose the distance from it. Let's say vertical force was -5. The distance is 2.5 meters from the starting point, and we look at this. For the global and local, let me show you. If I add a vertical force with the distance from it 2.5 meter, if it's respect to global, it means it respect to the whole axis. So it's not perpendicular to the member. If you want it to be perpendicular to the member, you need to let it respect to the this respect to this member. So we can just edit it from global to local. And now it is perpendicular to the member. Now let me solve an exercise that use member tab, support tab, hinge tab, join load, point load. I will be solving problem 3.13 from Fundamental of Structural Analysis, 5th edition by Kenneth Amlit, etc. So now I will be adding this exercise into PermaLearn. As it is already in SI unit, I don't need to change it, but I need to change the grid size. Now I have finished at the exercise. I still have support and point load and hinge to put. So, but not now. Let's check this first. So yes, everything is correct. So let's just go ahead and add the support. The here and here are all pins, so we can just put pin. So we put pin here and we put pin here. Now we have to put hinge for all the member. Just click one by one and add it. So now we have finished adding pin, we have to add join load. So I will show you how to use it. So we have a 12 kilonewton load at this point. So we just choose this. Here, and we could add -12 since the load is downward. Now it is correct. Now I will show you how to add this by using point load. So this is, we have to choose the member, which is thing, no member, yes, wait, I think member 8, yes, member 8. For distance from join, it is 1, no, it is 2 meter. We got a horizontal force of -18. Now we got everything, we can add it. Now everything is finished. Let's go to the solution tab. And the exercise wants us to determine all reaction. So we want to find AY and GY. For this one this is to display the member. This is display the support, the load, and the external effects is for the temperature change, fabrication error, and support settlement. So now let's display this. You can choose which member you want to see and which member you don't want to see. Like this, when you click it, you can display it, and if you want to see it, you put it back. Now let's moving on to the solution. We can find the reaction force right here. So we got AY equal to 12 kilonewton and AX equal to 9 kilonewton. For Gx, we have 9 kilonewton to this way. For Gy, it is equal to 0. That's why we don't have it here. And for normal force, it is the force of the bar, like this one. If we can zoom it. Let me zoom it for you to see. Or you could just like remove some member to see the force that you want to see. Let's say I do it like this, and this one it is compression. For the positive one, it is tension. We can also use shear. Since this is a thrust, the shear is 0. We can also see the moment, bending moment, reverse, and deformation. This is the deformation of the thrust, how the structure will change when the load apply on it. For Mengchhay, it is just an interval from one point to one point like this one. If you want to see the value more accurately, you just do this. Okay, now we could see it like the interval is really small. When you want the formation or bending moment normal force, it is more, the interval is more small, so the number is more accurate than before. Now let's go to linear distributed load tab. A linear distributed load is a load that spread continuously along the length of a structural member rather than a single point. It can be uniform distributed load or non-uniform like a triangle. So let's say we let's find a straight one just like this. A vertical or horizontal depend on the exercise. And if you want a uniform one, just put the same number and you get the uniform load. And if you want a triangle, you just put 0 at the beginning point or the end point. Like this one, this is the linearly distributed load. And now I can finally explain the cross-section load. Now let's refresh the website. The cross-section tab defines how the it changed. No, no, like the cross-section tab defines the geometric property of structural members. This property control how stiff or flexible a member behaves under load. In 2D structural analysis, the most important property are cross-section area, model of elasticity, moment of inertia. But for exercises that don't have A, E, or I, we can just ignore them and go straight to the member tab. Now let's solve some exercise. So now we will be solving the problem 940. It is determine all the reaction for the frame in figure 940. Given IAB equal to 600, IBC equal to 900, and the E equal to 29,000, and neglect the actual deformation. So we need to find the reaction force at A and C. So we will be using the distributed tab and the cross-section tab. So now let's start. So there is 600 and 900, so we need to add 2. 600, 29,000. For cross-section part, you need to put some number. You can just put one, but sometimes it could be a bit different from the solution, so we can put it the same as the moment of inertia. Now let's go ahead and add the member. Well, look like we make a mistake here. We forgot to change the unit, so we have to refresh everything and put it in BG because the exercise is in British unit. And we also need to change the grid. So now we need to go to the cross section again and add this value. Now we can add members. Oh, we also have to select the, the cross section. So AB is cross section with inertia 600. So this is the cross section one. For this one, it is cross section 2. Now we have to add the support. It is our pin. Now we have to add the distributed load. It is the second member, and with the load type vertical. So minus 2, minus 2. So now we are finished. We can go to the solution to check the answer. Slide we have AY equal to 34.28. The AX is equal to 8.57. The CY equal to 25.71, and the CX equal to 8.57. Now let's move to fabrication error tab. Fabrication error means a member is slightly longer or shorter than intended. Now let's take a look at this exercise 941. Assuming the load is removed, compute all the reaction for the frame with this figure if the member BC is fabricated 1.2 meter too long. Alright, so now let's go and remove the force, and we go to fabrication error, choose member 2. Since it is too long, then it is positive 1.2 inch. Now we can go to solution and find the answer. So we got AY equal 2.3, AX equal 4.6. This one is the same, and this is the answer for this exercise. And don't worry, the answer are correct. I already checked with the solution. Now let's go to support settlement part. Support settlement occur when a support moves settle vertically, horizontally, or rotate due to foundation movement. It means the support does not stay at its original position. So let's take a look at this exercise. Problem 9.44. Recompute the reaction of the frame in this figure. If support C settle 0.36 inch, support A construct above its original position by 0.24 inch, given E equal to this and I equal to that. So let's change the standard and expand our grid size. Then we add our cross-section value. Cross-section area equal to moment of inertia in order to get accurate result. So now we choose cross-section ID, and we just add the member. Now let's go to support. A is fixed, C is roller, Now let's add join load and let's go to support settlement. So A is go above the original position by 0.24 inch, and C settle 0.36 inch. And that is it. Then that's it. Now we get our solution. So we got AY equal 0.78 keeps the moments 33.36 and the AX equal to 4. And for this one, CY is equal to 0.38 and there's no CX. Oh wait, it's a roller so it doesn't have CX. Now let's move to temperature change. Temperature change in structural analysis refer to the expansion of a structural member caused by variation in temperature. So let's move to an exercise. 9.47 determine all reaction in the rigid frame. In this figure, in addition to the applied load, the temperature BC increased by 60 Fahrenheit given inertia equal to this and that, and we got alpha and we got E. So let's refresh the page and add our exercise. So we have to change the unit and the grids. Oh, that's not my bad. So we go to cross section, we get add this is for AB, and CD, and the E is 30,000. We put the cross-section area the same as moment of inertia for accurate result. So right now we can start with our members. Since AB is the same as CD, I'm going to add them separately. This cross section ID 2 and 48. Now let's add the distributed loads. It's vertical minus 1.6. Oh, I forgot to add support. It is all pin. So now let's add temperature change, which is the member BC by 60 and this one 6.5. Since it's got the same 10 power minus 6, we don't need to convert. And for this one, this is just a display problem. It should be Fahrenheit when you don't need to convert to Celsius, it's in Fahrenheit. So just put the Fahrenheit in here and you will get the same answer as solution. Now let's add it and now let's go to solution. Let's see the reaction. We got ay equal to 38.4, ax equal to 7.25, dx equal to 7.25, and dy equal to 38.4. So this is it for the solution. Thank you for watching. Goodbye.